equals pj. Is that?
Okay, let's see.
Yeah, so I guess it's a.
So utility is just pj.
Yes. That's what it says.
Okay, let's think about it. So basically, you have a Hamiltonian system, you have a flow, right? So what is the flow? Basically, it's a solution of a Hamiltonian system. Your xp become functions of t. This is the solution, that's the flow. And then you apply that map c to it, according to the, well, that you get your function phi, where x and p are all those solutions. And then you apply the map c, and you get that on the right-hand side. So basically, you get another flow, well, x over there, and then that p. And so he says that it's the same as if you would have solved the Hamiltonian system with a different function, namely u tilde, which is just pj. Okay, what is the Hamiltonian flow with ujb equal to pj? Well, what's on the right-hand side? H of u tilde. Can you compute it?
I believe that is computable because everything we've done so far has been constructed with the quadrature.
Well, but it must be trivial. What I'm trying to say is, what is the Hamiltonian? Okay, what is in general? What is that Hamiltonian vector field? H of u. Can you write it? That's the right-hand side of the Hamiltonian equation.
Yeah, that is H U J equals.
Well, you don't need tilde. Just okay.
That?
So go ahead.
I think it's that vector field.
Well, but not only that. It's two-dimensional.
Right. And that's one dimension.
Well, okay, let me remind what it is. So what is a Hamiltonian vector? Well, if you write it, the Hamiltonian equation, right? So there are two n equations, right? And so they give you, well, the right-hand side is a vector field. So you get d, well, in this case, du, well, there is j, let me call it, okay, duj by d. P I, and this is equal to negative du j d x. Okay, so that's the two-dimensional vector, which is that h of uj.
Is that dxi dp? Should that be
Where?
to the top left? To the
Yeah.
left?
Oh, this is t.
Yeah, t.
Sorry, yeah. Is that, so if you want to write it as a differential operator, then it's this times dx plus, no, not dx, d by dx, and then this times d by dt. Right, but that's this vector. Well, for this function, if uj is just p, then this will be delta and this will be 0. Do you see that? So the h of u tilde j, that will, well, this is equal to delta ji. That's the first vector, and the second is 0. So this has 1 and 1 in the place j, and this is just 0. So that's what it is. So of course the solution of that is trivial. If this is, well, the flow for that function is xi equal to, if this is delta ij, then it will be this delta ijt plus some constant, right? And this will be just some constant. So that's the point. I mean, you kind of that's the point of that map, to trivialize it. So this is just a shift. This is straight lines. You can, in other words, you can change your coordinates with some diffeomorphism so that the evolution is just a straight line. So p is constant, then x is just moves along a straight line. Okay, so, well, in general, you have some flow, right? They are moving somehow, they could be closed orbits, whatever, but locally, just look at that, change the coordinates and kind of make it straight. And then that's what this is. Okay.
So, actually, really quick question, I guess, with that, is that, since we do have a flow evolving on straight lines, is that related to, I guess, the method of characteristics?
No. Well, the Hamiltonian system is related because that's what Andrew was talking about. But you start with the PDE. There is no PDE here.
Right,
So
okay.
you start with the PDE and then you relate to it the Hamiltonian system, which is this basically equation of characteristics. The solution of that Hamiltonian system is called characteristics, and then you use that in a special way and you get a solution of the PDE. First order, only first order PDE, second order PDE, you cannot do that.
Okay. All right, so I guess now going over the example, they talk about then a specific example, or I guess in general they talk about the central force problem, which, as I mentioned,
Yeah, let's look at the example. Yeah, and by the way, well, is that the proof or is that, you wanted to show that something about quadratures, right?
yeah, I think they show that the linearization can be achieved solely through the quadrature, or it's generated by quadrature.
But is there anything after that, or just what, some kind of conclusion, or? So far you just stopped at, you said C maps one flow to another flow, okay?
Well, that actually does kind of seem to be their general conclusion there, I guess. They go on and do show that if you, in the specific example of dimension 2, where you only have one equation, or one u, then they show that you can explicitly construct an integral from that. I don't know if they're intending to say that that holds for any, 2n dimensions, but that,
Okay.
they don't seem to have a really.
Let's look at an example of this.
Okay. If you want, I could go through the two-dimensional case they talked about really quick.
What is example, is three-dimensional?
Well, the example is two-dimensional, but to talk about it in more general forms here first.
Well, let's do example, I guess.
Okay, so for the example, they talk about the specific example of the central force problem, which is the Kepler problem, which is essentially given that, so we have u of x equals, where I believe this is the energy of the system,
Potential.
or potential energy, and u = 0. And this,
I'm sure that you've seen it in your physics courses, like this is planetary motion. You have planetary, one mass in the center, and then there is another moving around, and that, well, you should get the ellipses.
yeah. And I guess this is actually an R4, but they then say that, so we have some function of position and momentum, but we then say that this is only a function of, that is not a function at all of the second y coordinate.
What is that better one?
Eta?
Oh,
Yeah.
well, usually it looks a little bit different.
Okay.
That's okay.
It's usually like that, I think.
Yeah, but a little longer down, yeah.
Okay.
But there is no that up.
Oh, really? Okay, I could have sworn it was a.
Yeah, that looks like, yeah, that's
Okay.
okay.
I thought it was.